In this webcast, I'd like to talk about line integrals and how you compute a line integral. First, we're going to go back and review what is an integral back in first semester calculus. The idea is you take a function from a to b, and you want to find the area under the function from a to b. To do that, you cut the interval a to b up into multiple segments. Each little segment, you say, has a width dx, and the height is f of x. So if you want a little bit of area, the idea is you take the width times the height, and you get a little bit of area. So if you'd like to find the total area, you add up little bits of area, which means you add up f dx, and since x are your bounds, you put an a and a b here. In this part, there's no bounds, so we could write we're integrating over the interval ab, and that's a possible notation when you have just a dA. So now, what we're going to do is we're going to extend this to be something in space. Suppose our function is something like 9 minus x squared minus y squared, and the curve, we're going to use the curve 2 cosine t, 1 cosine t, 2 sine t, so that I have an ellipse in the xy plane, and then in the space I've got a parabola, so there's our graph. I'll take that curve in the plane and we're going to go up to the function, and essentially we have kind of an ellipse with a non-flat top, so it's kind of like a cylinder, but it doesn't have a specified height. What's the area of this object? Well, the idea, cut the curve up into a bunch of little bits. Each little bit we now give the name ds to, and the height is still f. So if you want a little bit of area, you take the height times the width. If you want the total area, you add up the little bits of area. We're going to put c's down at the bottom to specify we're integrating along a curve. That is what a line integral is, and essentially it gives area of regions above curves rather than regions above intervals. At this point, we're actually going to compute a line integral to show how it's done. If you want to calculate ds, recall that ds dt is our speed. So anytime you see a ds, you have to calculate the speed and then multiply by dt, which means we're going to have to be calculating speed a lot. So the idea of our function is 9 minus x squared minus y squared, and the curve is cosine t, 2 sine t. Then we need to find the derivative, which is negative sine t, and then 2 cosine t. The speed would then be square this, so sine squared t plus 4 cosine squared t. And then if I want to integrate f ds, I need to integrate, if I'm going to go around the ellipse once, 0 to 2 pi would be my bounds. The function f is 9 minus x squared minus y squared, and then the ds is your r prime dt, so the square root, I'm going to put parentheses on there, square root of sine squared t plus 4 cosine squared t dt. Now the variable is t, which means the x's and the y's need to be replaced with what they are in terms of t. To find the x's and y's, you have to go back to our position equation, which tells us what x is and what y is. So there's our x and our y, which means I can go and replace the x with cosine t, the y with 2 sine t, then multiply that by the magnitude of the velocity, or the speed. Put a dt at the end, and then integrate from 0 to 2 pi. And many times we're just going to be setting up integrals because that integral right there would be extremely difficult to compute by hand. So we'll just set them up. Occasionally when you find one that's simpler, practice integrating it by hand, but otherwise most of the time we'll just set up. That completes this screenshot.